Talk about stoichiometry and energy. And to start with this, we've already discussed the difference between exothermic and endothermic, but that's very important to still understand. So let's get into that. Some reactions will release energy and some reactions will require energy, but regardless, there's always an activation energy, which we use EA as the symbol for that, that has to get the reaction going. Even if it's going to release a lot of energy, you still need to light the firework or the stick of dynamite or whatever it is to get it going. And this activation energy allows the reactants to reach what's called an activated complex, which is sort of the reactive species that can then go in either direction and is necessary to go forward as well as to go backwards. So if the activation energy is small, that means it would happen spontaneously. Not something we're going to worry about right now. But the point here is when you have reactants that have more potential energy than the products. So this H2 and O2 have more energy than the water. The reason the world is covered in water is because it's a low energy um, compound. Hydrogen and oxygen are hard to come by on Earth because they have more potential energy and they're so reactive. So water is less reactive than hydrogen and oxygen because of this difference in potential energy. When you get hydrogen and oxygen together in the perfect ratio and then you give it some activation energy, you will create water with a big boom. So to show you that, once I can find, there it is, that. So this video here will show you, I don't need that. So this is hydrogen and oxygen, and even though this is going to be a loud reaction, it still needs activation energy, which is why he needs to add the match. All right. So the point of that was that that's an exothermic reaction, even though it releases a bunch of energy. In this case, 572 kilojoules per 2 moles. Um, you still needed an activation energy. He still needed that match to get it going. All right. The reverse of this project process, when you start with water and you're going to hydrogen and oxygen, requires an activation energy that's going to be larger than the initial to go to water because you still have to get to that activated complex. And in fact, going in the opposite direction, now the kilojoules is positive because you're going to something that has greater um, potential energy. So going from water to hydrogen and oxygen gas would be an endothermic reaction. The products would have more energy than the reactants. And that's why when we did this in class, you can um, right separate water into its component parts by I love this new thing. There we go. All right. So you can so if you put a battery connected to water here. And then once that battery gets going, you can see hydrogen and oxygen are forming. You can tell which one's which because there's twice as much hydrogen as oxygen. So you can see this one is going at a much faster rate than that. And this will fill up at twice the rate of the other one because it's hydrogen and the other one's oxygen. So that is energy required, though. So all the energy you saw in that explosion in that newswoman's hands is now what has to get put into this water to make the hydrogen and oxygen happen. All right. So the point of all that is, and then a catalyst would lower that activation energy, which we talked about in a different thing. All right. So the point about all this is you can be given a balanced equation with a delta H. And if that delta H is negative, that means the reactants had to have more energy than the products because energy had to be released to get down to that lower um, threshold. And if it's endothermic, that means energy had to be put in. So therefore, the potential energy of the reactants would be lower than the products. Oops, H2 plus O2. There we go. Look at that. So in this case, water is at the bottom and H2 and O2 is at the top, right? So it's negative delta H. The difference between the potential energies is negative when there's more potential energy in the reactants. The delta H is positive when there's more potential energy in the products, because now you have to go up the hill as opposed to down the hill. All right, so this balanced equation tells you for 2 moles of water and 2 moles of hydrogen, if you only wanted 1 mole of hydrogen produced, how much energy would you need to release? Well, it would be half of that, and that should make sense. If every 2 moles of water will produce 572 kilojoules, 1 mole would produce half as much. So we're starting with 1 mole of water, and we know that for every 2 moles of water, there's 572 kilojoules. And that's how you do that. So it would be divided by 2 to figure out how much would get in 1 mole of water, and that is 286. So this would be 286 kilojoules would be released, or would be released. So you can make it negative. I'm not going to get too excited about that. You do need to know that negative is exothermic and positive is endothermic. All right. If you had 4 moles of hydrogen, so let's say, you needed to produce as much water as you could from 4 moles of hydrogen, and you assume unlimited oxygen, how much energy would that release? Now you hopefully understand that since you have 4 moles of hydrogen and the situation is still true that for every 2 moles of hydrogen, there's 572 kilojoules, right? Because for every 2 moles of this, there's 570 kilojoules released. So therefore, you would multiply it by 2. So 572 times 2 would be 572 times, of course, 572 times 2, 1144. All right. So anyway, yeah, just getting back to this. This is plus energy because it's released. So you get a bunch of energy at the end of this reaction. And this is plus energy as a reactant because you're trying to get up the hill. This is going to be plus energy as a product. Anyway, moving on. If you needed to make 1 mole of hydrogen, let's say you wanted to do hydrogen powered vehicles and you needed 1 mole of hydrogen. Well, for 2 moles of hydrogen, you need that much energy. So for 1 mole of hydrogen, hopefully it makes sense that you would need half that, because for 2 moles of hydrogen, you get 572 kilojoules. So remember, these equivalents are because this and this are equal. If you had 2 moles of hydrogen, you have access to 572 kilojoules. If you had 572 kilojoules, you could produce 2 moles of hydrogen. That's why we're allowed to keep them on top like that. So 572 divided by 2 is, again, 286. So it would take 286 kilojoules to produce 1 mole of hydrogen. All right. You can do this with grams as well. Just because this was all moles, that's all nice, but if we had 50 grams of water and we wanted to figure out how much energy is needed to break that down, we would consult our periodic table, and hydrogen has a mass of 1 and oxygen has a mass of 16, and there's 2 hydrogens in water, so 2 times 1 is 2 plus the 16, so water has a mass of 18 grams in 1 mole. So if 18 grams of water is 1 mole, and then we know that for every 2 moles of water, we need, or we can get 572 kilojoules. Grams cancels, moles cancels, and then we have kilojoules. So we're able to turn grams into kilojoules by doing the same thing we were doing before. So 50 grams is 2.778 moles of water. And so then divided by 2 and times 572 means we have 794. So you would need 794.4 if you need that kilojoules to break down 50 grams of water. All right. So that is the point, that when you have a balanced equation and an energy source, the equivalent is the energy and the moles of that situation. So here, nitroglycerin, if you're my age, you saw all sorts of Looney Tune cartoons, which had nitroglycerin. So here, nitroglycerin was all sorts of fun and games with Bugs Bunny and Wile E. Coyote. Um, so the reason nitroglycerin is so dangerous. Okay, so nitroglycerin is very explosive, as you can see there, as well as the TNT. I mean, it's hard to really figure out what was doing the damage. But anyway, all right. So nitroglycerin is so explosive because it produces lots and lots of gas for that liquid. That liquid can turn into lots of gas quickly, and that's what makes it super explosive. So if you balance the equation, you would see, and to help you with that, that would be 4 nitroglycerin. So if you have 4 nitroglycerin, 4 times 3 is 12. You would need 12 carbon dioxides. 4 times 5 is 20 hydrogens. All that hydrogens is going to water, so that would be 10 waters. The 4 times 3 is 12 nitrogens, so that would be 6 N2s. And then after you do all that math, you would see you have 1 O2 left. So that's why you needed 4 nitroglycerin. So there's your balanced equation. You would expect the energy to be a reactant or a product. Did he have to put energy in or get energy out to make that gas? And energy came out clearly because there was that big explosion. So this would be energy as a product. And it turns out it's 22,880 kilojoules per 4 moles. So if you only had 1 mole of nitroglycerin, not 4, does it make sense that if you had 1 mole, so if you had 1 mole of nitro, and we know that 4 moles of nitro will give us 22,880 kilojoules of energy, that 1 mole would basically give you 1/4 of that. So 22,880 divided by 4 is 5720. So that would give you kilojoules in 1 mole. And the diagram would be such that because this energy was released, that this had higher potential energy. So the nitroglycerin would be higher energy than all that gas. You need a little activation energy. In the case of that video, it's the train hitting the cart. And then when that happens, you get all the energy released, that 22,880 kilojoules.